We have been discussing on some examples of the use of the finite volume method for diffusion type of problems. Let us look into one more example where, unlike the previous cases, we try to discretize the governing differential equation in a cylindrical coordinate system. So, if we consider the example of a one dimensional steady state heat conduction in cylindrical coordinates. So, in cylindrical polar coordinates you could have r, theta and z as the 3 coordinates. So, what are the r and theta coordinates? If you consider a reference line and you consider a point, the point can be represented by an angle theta and a radial distance r, which are basically the polar coordinates. And on the top of that, if you have an axial coordinate, then it becomes r theta z, or the cylindrical polar coordinate system. Now here we are considering a case when it is a one dimensional variation. First of all, we consider the z direction to be large, so that there is no variation along z, and it is axially symmetric, so that there is no variation with respect to theta. So only there is variation with respect to r. The governing differential equation becomes 1 by r ddr of r k dt dr plus s equal to 0. So this is the equation that we are now interested to discretize. Now what is the first step in the finite volume method? We integrate the governing differential equation over an elemental control volume. So what is an elemental control volume? Say if it was a 2-dimensional system or a 3-dimensional system, then if you consider that there is a radial coordinate r, and you have an element of width dr, and let us say this angle is theta. So what is the dimension of this element? So one of the lengths, so we are talking about this element, one of the lengths is dr, the other length is r d theta. So you have the total length, or rather the total area of this shaded region as dA is equal to r d theta dr, because for small dr this is approximately like a rectangle. If you consider an elemental length of dz along the other direction, then the elemental volume r d theta dr into dz. Now in our case we do not have variations with respect to theta and z, but even if you consider that, it will remain inconsequential. So in our case, what is that which varies? So if you consider this dV, it has 3 parts. One is r dr, which is due to variation in r, then d theta, then dz. So, integrating the governing equation over the elemental control volume is as good as multiplying this equation by RdR, because there is no theta or z variation, or even if it is there, it cancels from all the terms equally. There is no specific variation. So, what we do is we multiply by RdR and integrate it with respect to R. Again we consider the radial direction, say this one, where the grid points are P, E, W, faces of the control volume are small e and small w. So, we integrate it from R small w to R small e, which is the control volume, and the length of the control volume we say is delta R. So, what we can see here is a very interesting thing, that because of this multiplication by the RdR term, when we evaluate the integral, this 1 by R singularity of the governing differential equation goes away. This is one of the intrinsic advantages of the discretization using the finite volume method. See, in any other method you have to bother about what is 1 by R at R equal to 0. You have to treat it in a special way, because it at R equal to 0 it is singular. But here you do not have to care about what happens at R equal to 0, as if you are starting with R tends to 0 plus, and in that condition no matter whatever the value of R is beyond 0 plus, you can cancel 1 by R and R, so that the effect of 1 by R does not remain. So, with that understanding you can integrate this term. So, let us integrate this term. So, integral of that becomes Rk dt dr from small w to small e, plus let us assume that S is a constant, or at least S is a function of temperature, where the temperature dependent term is given by Sc plus Sp into T. Sp into T is the temperature dependent term, and for that we assume a constant temperature over the control volume. So, we can write this as Sc plus Sp into Tp integral of R dr. In the next step we have to make a profile assumption for dt dr, or profile assumption for T to evaluate dt dr. So, what can be an acceptable profile assumption for T? Piecewise linear between the grid points. So, let us make that choice. So, if we do that we can write this as Re Ke into Tp minus Te by delta Re. Let us mark the dimensions. This is delta Rw, this is delta Re. So, that sorry, this is Te minus Tp by delta Re minus RW KW TP minus TW by delta RW plus integral R dr is R square by 2. So, R e square minus R w square by 2 equal to 0. You can organize this equation in the following form: AP into TP is equal to AE into TE plus AW into TW plus B, where what is AE? RE KE by delta RE AW RW KW by delta RW AP is equal to AE plus AW minus SP into RE square minus RW square by 2, and B is SC into RE square minus RW square by 2. Okay. So, the purpose of casting the equation in this form is to show that eventually you get the same form of the discretization equation, no matter which coordinate system you use, just the coefficients change depending on the coordinate system. If it was a spherical coordinate system, it would have been 1 by r square ddr of r square k dt dr, and then you have to multiply it by r square dr instead of r dr, considering the elemental volume in a spherical coordinate system. Now, let us move further ahead. We have till now discussed about steady state problems, but we are also interested about unsteady state problems, and many interesting unsteady state problems occur in physical reality. So, let us try to discretize or see the discretization of the diffusion type of problems considering the unsteadiness of the governing equation. So, now we will move on to one dimensional unsteady state diffusion problems. And we are still considering the finite volume method for the discretization. So, finite volume method for one dimensional unsteady state diffusion problems. Let us start from the general governing differential equation. So this is the governing differential equation. Now it is a diffusion type of problem, so the fluid flow velocity is not there that means this term is 0. Further, because it is one dimensional, this will become ddx of k dt dx, not ddx but partial derivative now, because t is now a function of both x and time. So we can write the simplified governing differential equation as we consider an example with s equal to 0 just for simplification, because our objective is not to show how to discretize the source term, that we have already shown through the examples of steady state problems. Now our objective is to specifically show that how to take care of this new term which has appeared because of unsteadiness of the problem. So the first step will be what? We have now two terms in the equation. One is an unsteady term, another is the conduction term. So what will be the first step? Integrate the governing differential equation over the domain, elemental domain. Now here the domain involves the specification of two coordinates, time and x. So when you integrate it over an elemental volume in the domain space will have elemental time also, dt and dx. So we have to remember that it is not a physical volume that we are talking about, we are integrating the governing differential equation over the domain. If the domain is a physical volume, then that is alright, but even if the domain is not a physical volume, it is the elemental space in the domain that we are considering. So we have a time space, we have a time coordinate and a space coordinate. So that elemental time into elemental space is a sort of element in the domain over which we are integrating the governing differential equation. That means we multiply it by dt dx and integrate. Now it is a double integral. Since it is continuous, it does not matter whether you integrate with respect to x first or with respect to t first. So according to the convenience of the terms, we either first integrate it with respect to x or integrate it with respect to t. So what are the limits? The limits of time are from time t to time t plus delta t, where delta t is the time step. So just like we have divided the x domain into a number of subdomains, similarly we are dividing the time domain into a number of subdomains, starting from time equal to 0 to then delta t, 2 delta t, 3 delta t, like that. So each small step is delta t, where delta t itself may be a variable. So one particular time step starts from time equal to t and ends at time equal to t plus delta t. So that is the elemental time domain. What is the spatial domain? Let us keep in mind the discretization P, E, W, small e, small w. So what is the x domain? from small w to small e. Right hand side x domain small w to small e, time domain t to t plus delta t. Let us treat these two terms separately, so that we consider this as term 1 and this as term 2. So, term 1 the term 1 has two integrals and we can split that effort therefore into two parts. First we calculate the integral in this red box and then calculate the remaining integral which is there in the green box. So, when we first calculate the integral in the red box, we consider the time to be a variable keeping the space coordinate unaltered, that is called as partial integration, just like opposite of partial differentiation. So, if we do that, then this comes out to be rho Cpt then del of that one. So, rho Cpt at time t plus delta t minus rho Cpt at time t, then integral of this one okay. Now here appears terms of the form integral of T dx, that is temperature dx. To evaluate that we must have a profile assumption that how temperature varies with x. What can be the simplest profile assumption? Constant, piecewise constant within each control volume, because you do not have to evaluate any derivative. So you can make such piecewise constant profile assumptions. So this will imply, so when t is a constant you can call it as t at p for each control volume. So rho Cp, let us consider rho into Cp as a constant. It could also be a function of position and you just had to integrate it by considering some profile, but for simplicity let us assume that rho into Cp is a constant. If that is so, that times, so this entire thing becomes a constant not a function of x, times integral of dx from small w to small e. So that times delta x. Next let us consider the term 2. To calculate term 2, again we have to calculate two types of integrals. First, in this red box where we calculate the integral with respect to x, and then the remaining in the green box. So when we calculate it with respect to x, what does it become? Okay. So the term 2 becomes k into del t del x at E minus k into del t del x at W times dt, integral of that from t to t plus delta t. So we require a profile assumption for t to evaluate the terms k dt dx type of terms. What profile assumption we can take? Piecewise linear between the grid points. So we can see that for different terms we can easily take different types of profile assumptions. We have earlier discussed that why we can do it, because at the end this history of profile assumption is lost once you evaluate the integrals. So the profile assumption is solely for evaluation of the integrals, you do not require this for any further interpolation or any other calculation, and therefore you have the flexibility of using different profile assumptions for different terms in the governing equation. Now you can write this as Ke Te minus Tp by delta Xe minus Kw into Tp minus Tw by delta Xw, where delta Xe and delta Xw are shown in this figure. Now integral of this with respect to t. Now here comes the important question. Here you have to evaluate terms of the form capital T dt integral of that. So there are 4 such terms, first 2 from this one T minus Tp and then second 2 from Tp minus Tw. So basically you require evaluation of terms of the form integral Te dt, integral Tp dt and integral Tw dt. So these types of things are required. So essentially your question is that you want to evaluate terms of the form integral of t dt from t to t plus delta t. So how to do it? It requires again a profile assumption for temperature over time. Just like you require a profile assumption for temperature over space to evaluate integral T dx, similarly you require profile assumption of temperature over time to evaluate integral of T dt. So standard profile assumption towards this is written in terms of a parameter f, which is a fraction, as follows. So it is f is a weight and it is considered to be some weighted combination of temperature at T and temperature at T plus delta T, if this is P. So in general, if forget about the subscript P, it can be temperature at any point. So we do not write P, it depends on which point. If it is P, we call it P, if it is E, we will call it E, or W, like that. So this is an intuitive profile assumption where we are dumping some weight on the temperature at T, some weight on temperature at T plus delta T. Remember, these are the two discrete points at which we know the temperatures, or rather we are to determine the temperatures. So the entire temperature variation within the time step from T to T plus delta T is considered to be a weighted combination of something that has to do with the temperature at T and some other thing that has something to do with the temperature at T plus delta T, some weighted combination where F is a weight. So depending on the value of this weight, we can have different schemes. So let us try to write the general form of the scheme, and then we will assign different values of F and see physically what it interprets. So we have Ke into Te minus Tp by delta Xe. So in place of Te, we will write 1 minus F Tet plus F Tet plus delta T. We will multiply all the terms by delta T at the end. This is P, right? Yes. This entire term multiplied by delta T. Okay. Now you have term 1 equal to term 2, and for notational convenience we write T at time T as T0 and T at time T plus delta T as T1, which we call as just T. So it is a notation, 0 superscript for the time at the beginning of the time step, 1 superscript for time at the end of the time step, and we usually drop the superscript 1 for just writing convenience. So if we do not use any superscript, we mean that it is the end of the time step that we are talking about. So, if you have term 1 equal to term 2, then we have AP into TP is equal to AE into TE plus AW into TW plus AP0 into TP0 plus B. Let us complete the evaluation of these coefficients and then we will see what are the implications of this new coefficient AP0 which has appeared. So, what is AE? AE is KE by delta XE into 1 minus F, sorry not 1 minus F but F KE by delta XE into F. What we will do is we will divide both the sides by delta t, so that we will write delta x by delta t here and that delta t is taken care of in this way. So, KE by delta XE into F, that has come from which term? That has come from this term. Then any other coefficient for AE? No. Then AW similarly KW by delta XW into F, that is from here. No, it is not minus, it is plus, it is coming from this term, okay. Then AP AE plus AW, then plus something, we will write that plus something, then let us first write what is AP0. AP0 is the coefficient of TP0. Where is TP0? TP0 you have in both in term 1 as well as term 2. So, you have one TP0 here, another TP0 here and the third one here. And we have to remember that AP0 and TP0 they are in the same side as AET and AWTW. So, these two will be, so this will be minus effect, this will be a minus effect and this will be a plus effect because this will go in the other side. So, it will become rho Cp delta x by delta t minus Ke by delta xe into 1 minus f minus Kw by delta xw into 1 minus f. And then what is B? the remaining terms. So, Ke by delta Xe into 1 minus f Te 0 plus Kw by delta Xw into 1 minus f Tw 0 then and AP as AE plus AW what are the terms which involve AP? Let us identify. This is one term, this is another term and the third term. So, this term is AE, this term is AW and then rho Cp delta x by delta t. So, these two terms when they go to the other side they become plus and this is already plus, okay. So, even for the unsteady state problem we are able to write or discretize the equation in a form APTP equal to AETE plus AWTW plus AP0 TP0 plus B, where now a new neighbor has appeared. Earlier the neighbors were E and W, now there is a time neighbor. So, there are two types of neighbors now, one is a spatial neighbor. So, for the point P you have the spatial neighbors as point E and point W, but for the same point P at time t plus delta t there is also a time neighbor which is that at time t. So, that is given by this one, this term. So, it is the effect of the time neighbor at time t, and only one time neighbor we are considering, because whatever is at t plus delta t that is going to be influenced by what has happened at time t, but not what will happen at time t plus 2 delta t, right. That is why you can see that there are two space neighbors but only one time neighbor. Once you have this one time neighbor you have to find out its implication, that we will find out, and the implication of the time neighbor it depends on what is AP0. Before doing that let us consider some special cases for different values of f. So, we next discuss the choices of f. Let us try to make a sketch of the variation of temperature with time between time t to time t plus delta t depending on what value of f we choose. Let us say that the values of the temperature at the instants of these two times are T0 at time t and T1 at time t plus delta t. In between how it varies. So, now look into this formula. First let us consider f equal to 0. Remember here f lies between 0 to 1. So, f equal to 0 and f equal to 1 are some special cases. F is a weight. So, any weight that can be assigned to either of these temperatures is either a 0 weight or a 1 weight or something in between, but nothing less than 0 or nothing greater than 1. So the limiting case, let us consider what is the consequence when f equal to 0. So when f equal to 0, you see that there is no contribution of T1, there is only contribution of T0. So then integral T dt becomes T0 times delta T. So what is the implication? Physical implication is we have considered a profile as if the temperature has been throughout T0 over the time interval from T to T plus delta T. So it is throughout T0, but at the end it has to jump and match with T1 because that has to be satisfied. So this is f equal to 0. It is clear, f equal to 0 means the throughout the time interval the temperature is T0, but of course it has to assume a new value of T1 at the end, so it suddenly jumps from T0 to T1 at the end. So that is the profile. F equal to 1, f equal to 1 is the other thing, that it means that throughout the interval the temperature becomes T1. So what it does is suddenly it jumps from T0 to T1 and then remains T1 throughout. So this is f equal to 1. If you have a f equal to half as an intermediate example, then it is 50-50 combination of t at 0 and t at 1, and in between it can be interpolated linearly, so that this is f equal to 0.5. So these schemes, so you can see that accordingly you can design different time integration schemes depending on what value of f you choose. What value of f you choose is your matter of designing the discretization problem. It's your headache, but we have to see that how to fix it up or what are the plus and minus points of choosing different values of f. But once you have chosen it, you have to use that particular f for your discretization, and there are different limiting cases that we have identified, and accordingly there are different names of the schemes. If f equal to 0, this time discretization scheme is known as fully explicit scheme, or in simple words just explicit scheme. If f equal to 1, it is called as implicit scheme, and if f equal to half, it is known as Crank-Nicolson scheme. Let us try to figure out first the coefficients corresponding to different values of f and see that what is the consequence of such coefficients. So f equal to 0. If f equal to 0, you can readily see that AE equal to 0, AW equal to 0, AP is rho Cp delta x by delta t, that is there. AP0 is rho Cp delta x by delta t minus Ke by delta xe minus Kw by delta xw. B is equal to Ke by delta xe Te0 plus Kw by delta xw Tw0. So, you can write for that case APTP is equal to AP0 TP0 plus B. So, Tp you can explicitly express in terms of T at the previous time step. So, you can see that here in this Tp0 you have temperature at the point P at the beginning of the time step, that is at the end of the previous time step. In B you have Te0 and Tw0. So, what do you infer from here? That the temperature at the point P at the current instant of time, that is at the end of the time step, you can express explicitly as a function of the temperature at the same point at the beginning of the time step plus at the neighboring points at the beginning of the time step. So that Tp is a function of Te0, Tp0, Tw0 expressed in an explicit form. Okay. This essentially implies that if you know what is the temperature at a particular time, you can just march with time and find temperature at any other point at the subsequent times by explicitly expressing the equation as the value at the current time as an explicit function of the value at the neighboring points at the same point at the end of the previous time, and in this way you can just march ahead with time. So, you need not solve a system of linear algebraic equations, you can just consider one algebraic equation, from that you can calculate temperature at that grid point, then the next algebraic equation the corresponding temperature at the corresponding grid point. So, you need not consider them to be coupled as a system. So, you can treat individual equations and from individual equations you can obtain the corresponding values of the temperatures. Now, that is one of the very important advantages. Now, let us consider f equal to 1, then AE is equal to KE by delta XE, AW is equal to KW by delta XW, AP is equal to whatever AE plus AW plus rho Cp delta x by delta t, AP0 is equal to rho Cp delta x by delta t and B is 0. So, here what you can see is that the temperature at a current time you can write as a function of temperature at the current time at the other neighboring points. Okay. So, Tp now is a function of T now, Tw now and so on, so that you cannot explicitly obtain Tp now from this equation. You have to simultaneously solve for all the grid points the coupled equations to get Tp now from the system of equations, and you have to start of course with an initial condition that what is the value at time equal to 0. So, that means in this equation in this particular form Tp now is expressed as an implicit function, not as an explicit function of the temperature at the previous time step, and that is why it is called as an implicit scheme. The Crank-Nicolson scheme behaves in between, and in our next class we will see that how satisfactorily these schemes do perform based on your constraints over time step spacing and grid size spacing, that we will take up in the next class. Thank you.